Hi there! Some time ago I produced two videos on Pimoroni's Enviro Plus board, which adds environmental sensors to a Raspberry Pi. In these videos I looked at each of the sensors individually, and if you have not seen them, I recommend watching these first. Now it is time to put all this together into what I call the Enviro station. This is the first of a set of videos that deals with building this. We start with the enclosure, which I got from eBay, seller L-Top Electronics. It is quite nice, easy to work with and well ventilated. At this point it's important to point out that I decided to make my station for indoor use only. If you plan on weatherproofing it, you need to, of course, a different enclosure and consider a whole lot of additional design constraints. Which enclosure you choose is really up to you, but of course it determines the front panel and the hardware arrangements. If you recall, I decided to use the MPR121 as input device for the Enviro station and experimented with elaborate copper foil arrangements for the touch sensors. Since then I realized making the touchpads using adhesive copper foil cutouts was way too much work, and I decided to make a PCB instead. Starting with a schematic, of course, which in truth isn't much, because all you see are 12 sensor pads connected to a central connector. The real reason for making the schematic is, of course, making and assigning footprints for the PCB. I drew the outline of the front panel and the required holes for the Enviro Plus boards to scale using LibreCut and saved that as a DXF file, which can be imported directly into KiCad as a board outline into the Edge Cuts layer. Then it is just a matter of arranging the touch buttons and routing the tracks to create minimal capacitive coupling. As you can see, the tracks ends are all on the rear of the PCB on that green area with small SMD solder pads. It may become clearer using the 3D viewer. You can see how the big touch buttons on the front are connected to the 12 smaller pads on the rear. 3 weeks later, I received my board from JLC PCB, despite COVID-19, complete with a gift of a roll of tape. I was very curious whether JLC PCB had actually done my cutouts and the non-rectangular board, or if I had still to do cutting myself. The website isn't clear on that. They sure wrapped their boards very thoroughly. By the way, I just picked JLC PCB because I used them before and I was happy with their service. They are not sponsoring or anything, and I will try other manufacturers as well. Well, my Gather files obviously had the right information, the cuts are where they are supposed to be, and the board has the right shape. The shiny buttons look nice. I'm quite happy how this turned out. But of course the first big question is, does the Enviro Plus board fit? It does. I deliberately designed the cutout for the display a bit larger to make sure I could adjust the board slightly for the best alignment with the holes for the other sensors. The second question, of course, does it fit into the enclosure? The idea is that it replaces one of the plastic front panels that came with the enclosure. Yes, it fits nicely. The PCB is slightly thinner than the original plastic, so it feels a bit loose in the guide rails, but it will get an additional layer in form of a laminated front sheet later, which should improve the fit. To mount the Enviro Plus board and the Raspberry Pi, I decided to superglue 4 nylon screws to the rear of the PCB. If you clean the glue points on the screw heads and the PCB first using alcohol, the superglue connection is extremely solid. Here you can see my idea of connecting the MPR121 to the touchpads. These connectors have long angled tails that will solder perfectly onto the pads. I could only get 18-pin connectors, so 4 will have to be cut off. The soldering job done, and it was very easy to do. The trick is to hold the connector straight and true for the first solder joint, the rest is easy. Here's the MPR121 to go with it. The eagle-eyed will have spotted that this is not the same board I used in my previous tests, because that one had straight pins while these are angled. Rather than trying to unsolder the straight connector, I simply bought another board on eBay for less than £4 delivered. For the next section, we need to discuss the options for powering the Enviro station, in particular the problem of turning it off with no external display or keyboard connected directly or via a network connection. This mode without displaying keyboard is often referred to as headless operation. As you may know, the Raspberry Pi is actually powered from an internal 3.3 volt regulator which steps down the 5 volts coming normally from the USB power connector. The plus 5 and 3.3 volts is also feeding the Enviro Plus board and all the sensors and the LCD display. When you apply 5 volts to the Raspberry Pi, the OS boots, and it's fairly easy to make it auto start your application once the OS is fully running. So power on in headless mode is easy to solve. What are the solutions for turning it off? You could, of course, just turn the incoming USB power off or unplug the cable. That surely kills it, but unfortunately it may kill it in more than one way. Unix systems don't like the power removed without a proper shutdown to write all the changes to the file system. If you just yank the power, chances are the files get corrupted and eventually the system may not boot again without the SD card being fixed in another computer. Just for completeness sake, if your app doesn't use files and you move all the files written by the OS to a RAM disk, you may get away with this code method. However, in the case of the Enviro station, I want to use logging extensively, so this is not an option. The next method is to implement a shutdown command in your application software, indicated by the power button icon here. When activated, your app issues a shutdown command to the OS and then terminates. This is, by the way, the method I use in my PowerMon device I have shown in other videos. This provides a clean shutdown and halts the CPU, but leaves the Raspberry Pi still powered. As a consequence, the Enviro Plus, LCD and all the sensors are still powered as well. In this test, you can see the power consumption of the combined Raspberry Pi with the Enviro Plus. I am issuing the shutdown command, which you can see from the flashing light on the Raspberry Pi. When the light is off, the Raspberry Pi is dead, but the Enviro Plus is still drawing between 60 to 80 milliamps. At best this is wasteful when connected to mains, and at worst this would completely drain even a good sized USB power bank in 5 days or so. Not acceptable for the Enviro station. So after some research, I decided to add an additional hardware solution from Pimoroni called an on-off shim, shown here in lovely magenta. This board has its own USB power connector as well as a combined startup and shutdown button. To start the system, you must press the button briefly, which latches the electronic switch in the on position and connects power to the Raspberry Pi and by extension the Enviro Plus. For shutdown, you press the same button but longer, which alerts a small piece of software installed in the OS, which in turn then issues the shutdown command. The on-off shim monitors the state of the shutdown using a dedicated pin of the GPIO, and when finished, removes the power completely. This isn't the cheapest solution, but probably still beats putting a similar system together using your own components. That said, there are a few issues you need to be aware. The board has an onboard button and an LED, but of course this is no good because it's inaccessible inside the enclosure. While Pimoroni has added 2 pads where you can connect your own button, they have not done that for the LED, and you really want to see that because its flashes tells you if the system has recognized the requested shutdown and when it's complete. The second problem is that the board is supposed to sit on the GPIO connector, sort of sandwiched between the Raspberry Pi GPIO connector below and the Enviro Plus socket above, hence the name shim. This requires really tricky soldering, and I'm wondering whether this should actually be soldered or just inserted and gets its connection by being squeezed from below and above. I got it all wonky, and if I had to do this again, I would definitely try inserting it without soldering. Wonky or not, it works as it should. once the necessary bit of software is downloaded from Pimoroni and installed. I'm still using the onboard button. It definitely works and turns the power off completely. As I mentioned, the on-off shim button can be easily paralleled by an external button, but the LED is a problem, and unfortunately the installed Enviro Plus blocks normal access to the GPIO connector. In the end, I had to install a few patch wires on the Raspberry Pi leading from certain pins on the GPIO to pin headers superglued on the area where the unused mounting holes are. If necessary, these extra pin headers can be relatively easily removed without damaging the board. What you see here is the underside of the Raspberry Pi Zero with the GPIO down here. I installed 4 patch wires. The second set came actually much later and are for a buzzer, but we might as well get both covered now. The external LED for the on-off shim is connected to pins 1 and 11, that's 3.3 volts and GPIO 17. The buzzer is connected between pins 39 and 40 over here, that's ground and GPIO 21. Here's a view of the on-off shim LED patch. I had not considered adding a buzzer when I made this change. And here's the second one for the buzzer. The side view shows the 2 pair of pin headers more clearly. The sole purpose of these mods is to improve usability, but everything will work the same whether you do them or not. This button with built-in LED from ARS components is what I'm using for operating the on-off shim. It is available in a selection of LED colors, but I had the red version already in the spare parts bin. It needs 4 wires. The green pair in my version connects to the button pin header on the on-off shim, while the yellow and red pair with a resistor wired in connects to the LED patch pin header underneath the Raspberry Pi PCB. The buzzer comes from eBay seller Switch Elec as a pack of 5 for $1.99. It's for 5 volts, but still way too loud at 3.3 volts and draws a rather hefty 15 milliamps for being fed from a GPIO pin. Hence I put a 270 ohm resistor in series, which makes it just the soft beep that I wanted at a modest 1 milliamp, but don't take the 270 ohm as a gospel. It depends a lot on the buzzer and you need to experiment. If you make the resistor too high, it will simply not work at all. In my case, with this buzzer, anything above 390 ohms was a no-go. I put this whole thing on a little leftover Vero board, which can be mounted with that screw in one of the otherwise unused posts provided by the enclosure. The black and white leads connect to the buzzer patch pin header underneath the Raspberry Pi PCB. The particulate sensor sits on the rear panel in a small frame made from coffee stirrers. Originally, I had in mind to secure it with a rubber band, but the frame is so tight that it holds the sensor just fine. The datasheet stresses the importance to keep the incoming and exhaust air paths separate to avoid circular air flows. In my setup, the air is sucked in through the rear panel guided by the white duct and is simply exhausted into the enclosure, which has vents on top and bottom. You can also see a big hole with superglued screws left and right for the temperature sensor and 2 sets of holes for USB connectors. More about these in a moment. In case you wonder, the air duct is simply made from stiff card. For the USB connections, I went with these ready-made cables from Innov 8 Wholesale Limited. They are having a panel mountable micro USB socket on one side and a micro USB plug on the other. I put 2 in, one for power via the on-off shim of course, and the other for data. Having both allows me to run the station and plug in a USB stick via an OTG adapter into the second port for collecting data. And while we are at getting things from eBay, I decided to upgrade the Enviro Plus with a high accuracy temperature sensor in form of the MCP 9808 from Adafruit. From my previous Enviro Plus video, you know that the temperature reading available in the BMA 280 chip is completely useless if you want to know the ambient temperature. In those videos I used a TMP36 instead and measured its output voltage with a spare ADC channel. That works fine, but the TMP36 accuracy is typical ±1 degree Celsius, but can be as bad as ±3 degrees Celsius. A bit too much for me. The MCP9808 is a lot more accurate, but has an I2C interface. Here it is wired to the I2C bus as well as 3.3 volts and ground. Speaking of the I2C bus, apart from the MCP9808, there's one more device not on the Enviro Plus in need of power and I2C, and that is of course the MPR121 touch sensor. So I made 4 Y cables, one each for 3.3 volt, ground, SDA and SCL. These cables connect the 2 external boards to the power and I2C bus pin headers on the Enviro Plus board. Here you see the USB connectors and the MCP9808 temperature sensor in their planned position on the rear panel. The idea was that the sensor would be mostly exposed to the outside air, so the big hole you saw earlier. However, that did not work out as planned. The MCP9808 still picks up the slightly hotter temperature inside the enclosure, so the sensor reads too high. I speculated that this may be because it's still somewhat hit by the exhaust airflow from the particulate sensor. I put a temporary hood on it to shield it from the inside air. It is filled with insulation material, and while it helped, it did not completely fix the problem, because there's an unavoidable gap underneath the board caused by the solder joints. If you splurge out on a high accuracy sensor, you want the readings to be as accurate as possible. Well, this is the solution for now. The MCP9808 is now completely outside. Eventually I may construct something to shield it a bit. As for the USB connectors, it turned out the round holes were just not wide enough for some of the squarish connectors like the OTG adapter. So I had to widen those holes, and as this was done with half the stuff already mounted, it's not the prettiest job, but it works, and since it's on the rear, I don't worry about looks. Another unforeseen problem was the USB connector going directly into the Raspberry Pi. With the particulate sensor on the rear wall, there just wasn't enough clearance left for a straight micro USB plug, so I had to sacrifice a cable with an angled plug and splice the 2 ends together to get a new shorter cable with a panel mount on one side and an angled micro USB connector on the other. With that fixed, the hardware build is done. The enclosure that originally looked so roomy is actually pretty filled up now. I'm glad I did not try to put it into anything smaller. To turn on, you just briefly press the button. It will light up to show that power has been turned on, but then it goes off again. Unfortunately, until the Raspberry Pi completes its boot 30 seconds or so later and the display springs to life, there is nothing visible that the unit is now in fact on. You may want to consider adding an extra LED just to show that power is on. Anyway, to turn it off, just press and hold the button for 2 seconds. There are a few flashes showing the shutdown is in progress, and then power is off. Just when this video is about to finish, perfect timing. As always, you find additional information, the Gerbers for the front panel PCB, the software, and an operating manual on my GitHub page, links in the description. In the next videos I'm going to show how to do the laminated front cover, followed by videos on the software and operation. Thanks for watching.